Okay, so let me start off by mentioning some examples in ROS that I think will be very useful for you guys to go through. So I'll just put them up here on the screen, and I suggest you just write down the example numbers and then go through and sort of either work through them, read through them and try to kind of digest what's there and try to connect sort of the sometimes there's a word description and you want to connect it to the mathematics, to random variables, to stochastic processes. So that's definitely something that's going to help you with homework 1. So these examples right here, there's a random walk example. This is a classic. I'm sure you've seen it in 160A. In addition, something that we're going to spend time on later on is random walks on networks. So example 4.36. One of the most important ones is birth and death chains. I've mentioned this example before. So the Ehrenfest urn from the first lecture falls into this category. So is the modified urn from section 2. We're going to look at a couple of more examples of birth and death chains in this lecture. Let's see what else. What's this one? Coupon collecting problem. Definitely, this is from chapter 5, and I'll mention it later in lecture. So that's a chapter 5 example. Let's see if there are any more in chapter 4. This one, 4.37, is a good one to know about. Let's see, and this one, 4.25. So these are kind of quite a few problems to look at. If you look at all of them or just a subset, I think it's important to kind of work through what Ross does. All the solutions are sort of there, and you don't have to maybe kind of struggle with it on your own, but just kind of walk, kind of just go through it and see sort of some of the steps and some of the logic that Ross kind of puts together in terms of how he analyzes some of these processes. All right, but so before, like I mentioned, we're going to cover 3 different examples, especially focusing on first step transition analysis. But all this involves some definitions, right? The use of some definitions from Markov chain theory. And so, let me just quickly kind of go through sort of the very basics. I'll put a supplement note that will kind of go through sort of what notation I like and some more commentary on all this. But these are the kind of the must-know definitions. I'm sure you've seen them in 160A, but just to go through them again, right? So we've seen what a random variable is, and we'll establish kind of that in the examples to come in this lecture. But xk is a random variable when it's essentially a function from a set omega to some state space, and writing down the state space for every process is a very useful kind of first step to getting your head around a problem. Stochastic process is just a collection of random variables, and so if you take a collection of these and just put them together, indexed by time, you'll have a stochastic process. When this index k is discrete, which it is now in the case of Markov chains, right? The reason they're called chains is because there is this discrete index 1, 2, 3, so you're kind of chaining these variables one after another, and we'll talk a little bit about the probabilistic dependence from going as we go from one to another that makes them Markov. But the discrete time here, right, refers to not to the state space, which could be continuous or discrete, but it refers to the nature of time, right? So there are continuous time stochastic processes and there are discrete ones. This is a discrete time stochastic process, which is evident by the fact that you have a discrete index on the time subscript. So certainly you have to kind of be able to very quickly determine whether you have a Markov chain on your hands or not, right? And this is the definition, the probability that on the next step we're in some set A, and A here is going to be a subset of the state space. Given this entire history of the process, if that ends up being equal to this probability on this side, which is the same event, but conditional only on the current time, right? We're thinking of the current time as k, and we're looking at the probability of the next time step. If these two are equal, then you have a Markov chain on your hands. And in the next kind of 3 upcoming examples, we'll see exactly how to sort of make this determination. And then here there's sort of some some notation that I think will be elaborated on in the Markov chain supplement that I'm posting. So these are one-step transition probabilities. The one step refers to the fact that you're moving from time k to k plus 1, starting from x and moving to y, and that's why those subscripts x and y are the way they are. And one little kind of caveat here is that sometimes these one-step transition probabilities may depend on what time you're looking at, right, on the time k. And so when they don't, right, when it doesn't matter what time of day it is, right, when the dynamics or the probability law of this process don't depend on whether it's night or day or next year or this year, it only depends on how you're transitioning in one step, you can write them in this form, right, transitioning from 0 to time 1 from the same two states, from x to y, right? And in this case, this chain is called a time homogeneous Markov chain, and you'll see that most books, including Ross, focus predominantly on this time homogeneous setting, and there's a reason why for it. If you want to find out why, see example or problem number 3, or in problem number 3 that we're going to look at. Right there, I show you how to take any time inhomogeneous chain, one where these transition probabilities depend on time, and how to convert it into a time homogeneous chain. So with that, you're welcome to move on to the earned problem examples.